Hi, I'm Alan Garfinkel. I'm a professor in the Department of Medicine and the Department of Integrative Biology and Physiology at UCLA, where I teach math to freshman biology students. So, my basic message today is that by and large, we need to radically change the math that we are teaching in order to make it relevant for in demand careers. So, what we have found, and what a number of people have found, is that modeling and dynamics are the key concepts that all math students need to learn in order to carry them into careers. And that in particular, the math that we need is not calculus as it is traditionally taught. And I'll talk about that. And the thing that we have found through practice is that a course on modeling and dynamics, which would be based on 20th century math, not 19th century math, is possible and desirable. And we are currently teaching it to 2,000 freshmen a year at UCLA, not to mention other campuses. So I'm going to focus, I'm in medicine and physiology, and I'm going to be focusing mostly on health professional related things. I will talk a little bit about economics and management. I will not have, I don't have time today to talk about engineering, where I believe these same lessons also apply. So if we look at medicine and the health professions, what do we see there? The big thing that we see there is the omnipresence of feedback loops. You have a meal and it raises your glucose. That raises your insulin secretion by the pancreas, but insulin secretion lowers glucose levels by metabolizing the glucose. So we have a negative feedback loop. The gonad releases hormones in response to instructions from the brain, but those gonadal hormones then have negative feedback on the brain. Body temperature rises and physiological responses like vasodilation occur to bring temperature back to normal. So body temperature is controlled by a feedback loop. So what do we need in the health professions? Well, we don't have to guess. The health professions have told us what they want and what they need. Here's a 2009 call from the Howard Hughes Medical Institute and the American Association of Medical Colleges. That is the US medical schools. And they put out a brochure in 2009 called Scientific Foundations for Future Physicians. So this is what the medical schools want. They want certain undergraduate competencies. And the first of them is that students be able to quantify and interpret changes in dynamical systems involving positive and negative feedback. They want the student to be able to explain how feedback leads to oscillations, for example, in glucose levels. They want the student to be able to use the principles of feedback control to talk about health and disease. So this is the medical schools talking. They want feedback and dynamics. If we turn to epidemiology, a subject very much in the news these past years, again, we see negative feedback loops and some positive feedback loops, but in particular, the key negative feedback loop, which is that we have a susceptible population, and that positively impacts the infected population, but then the infected population lowers the susceptible population. So we have a negative feedback loop. We turn to the study of ecology, and we have negative feedback loops. Prey increase the number of predators by feeding them, but predators decrease the number of prey. We have positive feedback too. Juveniles increase the number of adults, but the larger the number of adults, the more the number of juveniles. So there's a positive feedback loop. And even in economics and business, what we see is feedback loops. Demand in the form of dollars increases the supply, and the supply then reduces the demand in a negative feedback loop. In management, orders increase the shipment of product, but the shipment of product then decreases the orders by filling them. So feedback loops are everywhere. And the question is, what kind of math do we need to study feedback loops? And the answer is feedback loops can only be understood through modeling. This is the first slide from the first day in our class to freshmen. And we say, put a bunch of sharks and a bunch of tuna in a big patch of ocean. What happens? And they say, well, the sharks eat the tuna. And you say, yes. And then what happens? And they go, oh, yeah, then you have a lot of sharks and very few tuna. That's not a stable situation. So dynamics has to be understood through modeling. But don't take my word for it. This was another call. Vision and Change was put out by the National Science Foundation and the AAAS 12 years ago. And what do they want? They want modeling, computation, modeling, dynamics, modeling. This is the National Science Foundation talking. This is what our students need. Now, what kind of math does the student need? It has also been addressed. And this, I think, is an extremely important point to make. The National Academy of Sciences, no less, put out a brochure all around the same time. And notice what they have to say. Mathematical methods should be taught, but on a need-to-know basis. In other words, don't tell me you have to memorize that the derivative of secant is cosecant or whatever it is, because 2 years from now, you'll thank me because you're going to need it. That's bad teaching. Then they say the emphasis should not be on the methods per se, but rather on how the methods elucidate the biology. That is an absolute rejection of our standard freshman calculus class, where the focus is indeed on the methods per se, and years from now, you're going to use this, maybe, except you're not. So what is the math? The math is ordinary differential equations, but notice something. Don't think, oh, they have to take a class in Diff-EQ, and if they take a class in Diff-EQ, then they have to have calculus. In order to have calculus, you have to have pre-calculus. No. National Academy of Sciences, no less, says ordinary differential equations without any formal course in differential equations, made tractable and understandable via Euler's method. So this is a very, very clear set of calls from the National Science Foundation, from the National Academy of Sciences, from the American Association of Medical Colleges. These are major institutions. And you would have thought that with such a clear statement, there would be a rush to design courses like this, but there has not been. And I think that's a problem. So our deans and us decided to design a class, which is given in the life sciences. It's called Life Sciences 30. It's taught to freshman biology students. So these are 3 months out of high school. There is no prerequisite, no calculus, no pre-calculus, no pre-pre-calculus, no college algebra, no prerequisite. And for life sciences students, it replaces the traditional calculus class to satisfy our quantitative reasoning requirement. So what do we do in this class? Well, we start with sharks and tuna, and we say, how do we understand what is going to happen to the sharks and the tuna. So we learn we're going to make certain state variables. S is the number of sharks, T is the number of tuna. And then we're going to make a shark compartment and a tuna compartment, and we're going to ask what makes sharks go up, what makes sharks go down, what makes tuna go up, what makes tuna go down. And then the all-important shark meets tuna term, which accrues to the benefit of the sharks and to the deficit of the tuna. So we have these terms, and we collect them all into a boxes and arrows diagram. And then we turn that boxes and arrows diagram into a change equation. And the change equation just says the change in the shark population is, and we collect all the positive terms with positive signs, and we collect all the negative terms with negative signs, and we get a change equation. Now, once we have a change equation, now the question is, what do we do with this? Okay, we have this model. The model is a change equation. What do you do with a change equation? Well, the one thing that we do not do with a change equation is any kind of symbolic manipulation. We do not substitute variables. We do not do integration by parts. Don't touch the change equation. The change equation is there simply to give us change vectors because, among other things, the shark tuna equations have no paper and pencil solution. You can't integrate this simple differential equation. This represents calculus fail. If you got an A++ in standard calculus, you cannot touch these equations. And so all traditional calculus, if you can hear the quotes around it, all calculus goes out the window on the first day of class. And all of those procedural tricks, which I'm listing here, have absolutely no application and go out the window on the first day of real life. So I think we have to face the fact that a lot of calculus is what I call calculus from hell. And what's a good diagnostic test if the student has taken calculus from hell is just ask them what is a derivative. And if you get an answer like, oh yeah, the derivative, I took calculus, the derivative of x squared is 2x. You put the exponent in front of the variable, and then you have to drop the exponent by 1. That's bad teaching. I'm sorry. That's procedural tricks, not concepts. I got to laugh at the fact Mike Reed is still an excellent mathematical biologist at Duke and is very active. He said this in 1987. The first problem on the exam was differentiate x to the sine x. And I said, that's what's wrong with calculus. Why should I spend all my time worrying about how to differentiate stupid looking functions like that? Well, it's 36 years later and nothing has changed. So we do things very differently. We deal with the change equation as an unmodified expression, and we view it as a machine for spitting out change vectors, S prime, T prime, for any given state, ST. In other words, what the change equation is saying is, if you are at this point, 10, 20, 10 sharks, 20 tuna, head northeast at a speed which is the direction of the change arrow, the change vector. And the length of the change vector indicates the speed with which you should move. So in order to make this rigorous and as a very powerful teaching tool, we need 3 20th century concepts, not symbol manipulation and formula manipulation. The first key concept we need is the concept of state space. So this is a space in which, in this case, it's a 2-variable system. So we have a 2-dimensional state space. If it's a 5-dimensional system, then we have a 5-dimensional state space. And we have simple rules for manipulating vectors, which are n-tuples in state space. So we simply need to get across the concept, and a very deep concept, that the system state is a point in state space. The second key concept we need is the idea of the space of change vectors. Change vector space is also called tangent space. And tangent space has different axes. It's S prime and T prime. And a vector in tangent space is a vector T0 prime, S0 prime. It's a change vector. And then the third and the magic concept, and if you take nothing from this talk but take this slide. What is a change equation? In 20th century math, a change equation is a vector field. And a vector field is a function from state space into tangent space. And given a point, T0, S0 in state space, the vector field assigns you the appropriate change vector, T0 prime, S0 prime, which is an element of tangent space. So this is the key concept. This is what a change equation does. It assigns change vectors to every point in state space. Then we take those change arrows. So this has the units of tuna per unit time, shark per unit time. But we multiply it by 1 with the units of time. And that gives us something in sharks and tuna. And we can then write that change arrow right on the point T0, S0. So now we have a field of change arrows. And those change arrows are going to be like Google Maps or Siri. They're going to say, if you are at point T0, S0, head in this direction at this speed. So with the concept of state space, the vector field takes you to tangent space, and that then paves state space with change arrows. The resulting picture looks like this. And now you can immediately see what the ensuing dynamics are. You start from a point here and you're going to go around here and you go, oh, look at this, it's going, it looks like this populations are going to oscillate. And that's correct. Now, I was tracing this with the cursor, but of course there's a rigorous way to do that. And that is the Euler's method that the National Academy of Sciences was talking about. In which you simply start from an initial condition, get the change arrow, follow the change arrow for a very short time, delta t. That puts you at a new point, re-update, evaluate the change arrow there, follow it for a very short time. And in that way, you approximate the trajectory that is predicted by this change vector equation. If you do that with Euler's method, this is what you get. This is the trajectory predicted by the change equation. And the point I need to stress is there is no equation for the blue curve. Calculus is of 0 value in understanding this simple system, or understanding insulin glucose dynamics, or brain gonad dynamics, or susceptible infected dynamics. They are all essentially beyond the reach of the calculus techniques that we use. And what's more important is, in order to understand these, you have to throw all that calculus out the window. It's not a preparation to understand this. the first thing you have to do is forget everything you learned, which is that equations can be banged on with symbolic methods to produce solutions. That's a dead end. So if I said, this is a major conceptual difference. If I say to you, I'm integrating a differential equation, maybe this is the picture that comes to your mind, but it's not correct. And it's a very poor concept of what integrating a differential equation is. This is what integrating a differential equation is. So you say to me, oh, Alan, what are you doing here? And the answer is, oh, I'm integrating a differential equation. Look, I'm integrating this equation. And that's a very, very different concept. If you will, it goes to a different part of the brain than the left-hand side. Now, mathematically speaking, formulas, symbolisms, banging on formulas with rules, L'Hopital's rule, this rule, that is all math from the 19th century. And this is what we are largely teaching today, and this is what we need to stop teaching. 20th century math exactly gives rigorous definitions of concepts like state space, tangent space, and the vector field. And what we have found, and I think distinguished mathematician Ralph Abraham is the person who really realized this for the first time, the 20th century rigorous high math concept is better pedagogy for high school students and college freshmen than standard calculus. Now, of course, you have to have some way of carrying out Euler's method. And we give the students and familiarize the students with enough Python to be able to integrate this differential equation. And here is the code. This is not 5 pages of code. And we can take them through this line by line, and they understand what the code is doing. They understand how to modify the code. We don't ask them to generate the code because we are in the era of ChatGPT. So we want to familiarize themselves with the code and understand what the code is doing and how to modify the code. We do talk about the derivative. I believe that the concepts of derivative and integral need to be understood by everybody. So the question is a raging debate, who should take calculus? If you mean who needs to take integration by substitution of variables, the answer is no one. If you mean who needs to understand what a derivative is, understand the concept of a derivative, the answer is everyone. And what is the derivative? What our students learn is that the derivative is the linear approximation to a function at a point. And we can use, here is the linear expression, delta y equals m delta x, and m is the derivative of f evaluated at that point. So the concept of the derivative as the linear approximation to the function at a point is a very powerful concept, and we do teach that. And we even teach the students how to extrapolate over short distances using the derivative instead of the function. We also teach the concept of integration. If you have the velocity of a car, then one of these rectangles is the amount of distance equals velocity times time that the car traverses in a short delta t. And what you need to do to get the total distance is add up the little rectangles. So adding up the little rectangles is a very powerful concept. It's how you need to go from the daily COVID infection rates to the cumulative COVID infection rates. And you definitely need to understand that. So we do a lot of applications. I do want to just mention briefly one of our favorite applications. The MIT Sloan School developed a marvelous game, which they have CEOs in for summer school, and they play this game by hand. It's called the beer game, and we have 5 layers of player, and orders for beer go 1 level up the line with a 2-3 day time delay, and cases of beer come 1 level down the line. At every node on the line, we have a supply line, we have an inventory, and we have outgoing orders. We have a beer equation, and we have an orders equation. The beer equation is fixed, but the orders equation, you have this F where you get to set your ordering strategy as a function of your inventory, supply line, previous orders. In particular, you, the player at that level, get to specify the expected demand, how sensitive you will be to the expected demand, and if theta equals 0, then your expected demand on the n plus first term is simply equal to your expected demand on the n. You do not change at all. Your sensitivity is 0. But if you set theta equals 1, now you're totally sensitive to incoming fluctuations. And the question is, okay, consider this system, consider it in steady state. Beer is flowing in, orders are flowing out. Give a little perturbation, a little change in consumer demand. What is the behavior? Well, the behavior of this system is counterintuitive, but if you're familiar with supply chains, it's not so counterintuitive. If the desired inventory is 17 and your sensitivity is low, you will come to a steady state after many weeks, although missing the desired management target for inventory. If the sensitivity goes up, then you go into oscillation. As beer comes down the line, you shut down orders, so you have no beer. So then beer is a shortage. So then the orders go up. You can get oscillatory solutions, and at high sensitivity, you can even get chaotic solutions. And the CEOs at the Sloan School and students who play this game learn how to manage supply chains without inducing bad dynamics. It's a very powerful lesson. So that's an outline of our course. We have some wonderful educational psychology people at UCLA who have been following our class and doing surveys and follow-ups. And here are some very interesting outcomes. Student interest in math before taking our course. A lot of lows, a lot of mediums, some highs. But afterwards, the biggest barrier, the biggest column is high interest in math after taking the class. Our current enrollment is 2,000 students a year. We're a big university. We are 40% first generation college. And a lot of students take our class. Look at these outcome measures. This course increased my confidence in my math ability. 80% said yes. I saw the real life application of what I learned. 94% said yes. Then we had an objection when we developed the class that, oh, this class will not prepare students for subsequent courses in physics and chemistry. And the answer is, well, yes, it does actually. Our class versus the math department calculus class, these are their grades in the subsequent chemistry class after taking math. You'll notice that we have a lot more A's in chemistry than the students who take Math 3A, and they did controlled for various socioeconomic factors on this. Same thing in the subsequent physics class, a lot more A's in physics. Say briefly something about underrepresented minorities. Underrepresented minorities do much better. Our underrepresented minorities from the LS30 series do a lot better than at physics and get A's at twice the rate of underrepresented minorities who took math, the math calculus class. And finally, our DFW rates are running around 4%. We'd like to get that better. But 4%, I think, is pretty good. I go to meetings where I hear stories from my colleagues about there being a 40% DFW rate, a 50% DFW rate. And that is just awful. And that says we're not teaching the right stuff. So I just want to close. 2 weeks ago, we gave a workshop at Harvard led by Brendan Kelly, the excellent director of undergraduate math there, and Jennifer Choker from Texas State, where we had high school students taught by visiting faculty and young Harvard instructors. And the teaching these high school students went very successfully and they loved it. And just as a current update, all of these universities have now expressed interest or are actually already teaching versions of a dynamics and modeling class at their universities. So happy to take questions, and thank you very much for your attention. Well, there's an interesting question in the chat from Guillermo. Your description of old-style calculus as a collection of procedural tricks could very well apply to most K-12 math. And I have to agree with that. It's true. We are way too focused on this 19th century idea of formula banging and the idea that math should be used to represent real phenomena. You can do elementary modeling at the second, third grade level. You can have students acting out sharks and tuna. I think the real villain here is the idea that, are you good in math? And what good in math means, I'm very clever at seeing that if you take the square root of both sides, then that becomes the quadratic. And those are skills that are not transferable. They're not generalizable. They're not going to help you when you get to later real applications. And I think we really have to start doing some very elementary modeling at the 5th, 6th, 7th grade level. I've given a lot of 9 through 12 lectures that start with shark tuna or do other simple modeling problems, epidemiology modeling problems, where susceptible bumps into affected and the susceptibles go down and the infecteds go up. You can actually act those out. Modeling can be taught really after the 5th and 6th grade. And absolutely should be, and absolutely opposed to this idea that what good in math means that I manipulate formulas in my head. So that's what I think is really neat, is a rethinking of what is math. What are we doing here? And for example, the idea, I'm very obsessed with the idea that calculus is a dead end. When I say calculus, traditional Stewart formula manipulation calculus is a dead end. I mentioned that we teach that what is integration? Integration is add up the little rectangles. That's in one variable. And then when we're integrating a differential equation, it's adding up the little changes. That's what we need to do. We need to, when the student comes to my lab and we're modeling the onset of a cardiac arrhythmia in a 3D model of the heart, rules for differentiating trig functions have absolutely no application. We're doing simulation approaches to differential equations. Hangwan Guo says, at what age do you think this teaching is appropriate? And I think I already addressed that. The answer is sixth grade should not be a problem. And high school is no problem at all. I've done it. I've given lots of high school talks. I think people are doing this in high schools. And what is preventing this? Unfortunately, a very bad belief and social structure that says calculus is how you get into elite colleges. And of course, that is no longer true, if indeed it ever was. Harvard has no calculus requirement whatever, and they make a point of saying so in their application entrance requirements. The whole idea that calculus and who can take calculus and how do we get calculus to these people, I think is a misguided effort, because the calculus that we're talking about, symbol manipulation, is not appropriate and is unfortunately turning even young people off. Hangwan asks, for what future majors? So our life science division is physiology, molecular biology, uh, ecology and evolution, all of the life science majors. Um, but as you saw, uh, nonlinear beyond calculus phenomena occur in physics and chemistry too. And the chemical equation, turning those into differential equations, they're unsolvable by calculus techniques. Jill Barchet asks, would you improve the mathematical instruction in the algebra to calculus track instead of developing a new data science track for students? Yes, answer is yes, I would. This is not data science. This is what should replace calculus, in my view. And the sooner we start doing this and the lower the level we start doing this, the better off. So I'm in favor of radically reforming the algebra to calculus track.